I chose to attend because there are other talks that I think just being there in person really helps you engage and connect with people who have similar interests and even different perceptions. So it's just nice to be here in person.
Of C++23. It's already available in Chinese, and next year it will also be available in Korean. I'm also the founder of the Belgian C++ users group, and we try to organize like around 4 events every year. They are all free, and quite a few attendees are attending these. All right, so I'll be giving an overview of a lot of new core language and standard library features that are coming with C++26. The 26 standard is quite a bit bigger compared to 23. And this slide lists all the topics that I will be talking about today. Obviously, it's not possible to discuss all of these issues in detail in a 1-hour session, but that's not the goal of my talk. So the goal is to give you an overview of what is coming. You will have a lot of keywords that you can use to search for more information on the internet. As you can see, I have a lot of material to go through, so please skip your questions for the end if time permits. And in the lower right corner, there is a slide number that you can use to refer in your question. All right, let's start with the C++26 core language features. First one, it's a big one. It's one of the big ones that's coming with 26, is static reflection. We get an initial set of features to support static reflection. First component of that is a structure, a data structure, stud meta info, which represent program elements via constant expressions, and these are called reflection values. To create a reflection value from an operand, you use the reflection operator, and that's a double hat. Next to that, we have a whole bunch of const eval meta functions that work on reflection values. And finally, there is this thing called a splicer that creates a grammatical element from a reflection value, and you see there the syntax. Let's first look at a rather contrived example, just to show you the syntax. So in this first line, we are using the reflection operator to get information from type int, and we store that as a reflection value in R. Then we can use a splicer to define x, and the type of x will be the same type as the type that is stored in the reflection value R. In this case, x will be of type int. Of course, you can also combine the splicer and the reflection operator together. So here we're defining a variable c, and the type of this we query by using a reflection operator on type char, and then using a splicer. Of course, this is a bit convoluted. You're never going to use it like this, but let's look at a more useful example. So we want to write a function that gives you the name of an enumerator. In this example, we have here a color enumerator with 3 values. And what we want is, we want a function enum to string that just returns us the string of an enumerator. Or, if you give an invalid number, we want unnamed. So, to start, we write a Constexpr function template that accepts an enumeration E in this case. We constrain E to be an enumeration. And next, we use a template for to iterate over all the enumerators of the enumeration E. And for this, we use the reflection operator to get information about our type E. And we pass this reflection value to one of the new meta functions called enumerators of. That gives you a collection of all the enumerators. And we use a template for construct to loop over all these enumerators. Template for is also new in C++26. It's called an expansion statement, and that is a loop that happens entirely at compile time. So, what do we do in our loop? For each enumerator that we are looping over, we use a splicer to create a value, and we check if that value equals to the value that we passed in to the function. If it's a match, Then we use another meta function called nameOf to get actually the string or the name of that specific enumerator. If we don't have a match, we return, lost my pointer, we return unnamed. What is also new is that you can add annotations to your entities in C++. And these annotations can be queried using reflection. The syntax is a double square bracket equal, so it's kind of an attribute, except for the equal sign. And again, so in your reflection code, you can query for these kind of things. So you can do something special for a certain type that has a certain annotation. So this is a very brief overview of static reflection. There's much more to tell, many more meta functions and so on. So there are, in the lower right corner, there are 2 interesting sessions that you can attend or watch later if you're more interested in that. The second big addition to C++26 is contracts. This feature introduces 3 types of assertion. The first one is preconditions, postconditions, and assertion statements. So let's look at all 3 of them one by one. First, preconditions. These are assertions that need to be true when a function is called. And the most important use case for this is to make sure that the input values that are passed into the function are valid, or that member variables of a class are in a valid state for the function to work. And in this example, we state, or we require, that the input variable I is larger than 0. We can't just use unsigned int in this case because we require I to be larger than 0. At this moment, you cannot specify an explanation when an assertion is failing, but you can use this trick with the double ampersand, which you could use in the past as well with static asserts. And then, if you're violating this assertion, the compiler will output the string and makes it easier to see why you violated the string, the assertion. Next are postconditions. These are assertions that must be true when the function has finished executing. So in this case, we have a clear method on a myContainer class, and the postcondition of this thing verifies that the function has actually done what it's supposed to do. So when we call clear, if you afterwards call empty, it must return true, and this postcondition is asserting that. As you can see in the postcondition, or in any assertion, you can call other member function of your class. You can also assert or include the return value of the function in your assert. And you see the syntax here. So what this postcondition is doing, it defines an R, which is the return value of the function, and we can say, in this case, that the return value of the function must be larger than or equal to I. These precondition and postconditions can be combined however you want, and you can have multiple preconditions and multiple postconditions. The final kind of assertion are assertion statements, and these are assertions that you can put in the middle of your function when you want to assert anything. It's similar to the existing assert macro. Let's look at an example that combines everything. So we have a function f here accepting an x parameter. Precondition is that x must be not equal to 1. Postcondition says that the return value must be equal to x, and the return value must not be 2. And in the body, we assert that x is not equal to 3. Of course, this is a rather contrived example. It's slide code. If you call it with 0, there are no violations. If you call it with 1, we are violating the precondition. Calling it with 2, you're violating the postcondition. With 3, you're violating the assertion statement in the body of the function. And finally, if you call it with 4, there is no problem. Evaluating these contracts, there are 4 strategies that are defined in the standard. We have ignore, observe, enforce, and quick enforce. Ignore, the name is self-explanatory. All assertions are simply ignored. Observe, when there is a contract violation, then we call a so-called contract violation handler. And if that handler returns normally, then we continue execution of the program. Enforce, if there is a violation, we again call the handler. if the handler returns normally, we terminate the program. And quick enforce, if there is a violation, we don't call the handler, but we terminate the program immediately. This contract violation handler is called, it has a predefined name, it's called handle contract violation. The standard doesn't really say what that handler must do, but it recommends that an implementation outputs a diagnostic message. And whether or not you can replace this violation handler with your own, that is implementation defined. If you want to know more, there are 2 interesting sessions in the lower right corner that are happening this week. Next, unnamed placeholder variables. So sometimes you must invent some random name for an entity, and afterwards you never use that name anymore. So let's look at an example. If you use logguard, you have to give that thing a name, even though you will never use that name. Or sometimes you use a structure binding and you don't care about one of the bindings. So you have to invent the name before C++26. With 26, you can use the underscore placeholder as a kind of an unnamed entity. Before C++26, the second argument to static assert had to be a string literal, as you can see here. With 26, it can be any constant evaluated string. For example, it can be a string view from a const eval function. And what does this allow? It allows us it allows a couple of new use cases. The first one is sharing of strings. So I can define a Constexpr string and then use it in multiple asserts. Second use case is it allows for computed strings. This code right now doesn't work with C++26 yet, but once std format is Constexpr in a future standard, then you will be able to write code like this, where the static assert message is actually computed using a call to std format. Equal delete exists since C++11, not sure. But now you can specify a reason. So here we have a new API, and the old API function is deleted, and we explain why. An interesting use case here is if you have, for example, move-only types, where the copy constructor and copy assignment operator are deleted. You can add an explanation of why these are deleted. So in this case, we say copy construction is expensive, and so use move construction instead. C++26 introduces several improvements related to structure bindings. And the first one is that you can now specify attributes on individual bindings. Like here, maybe the introduced binding y is unused, so we can mark it as such using the maybe unused attribute. A second structure binding improvement in 26 is that you can now use them in conditions. Before, they could only be used as a statement on their own or in range-based for loops. But now you can use them in the condition of an if statement, a while statement, for statement, and switch statements. Let's look at an example. So here we have a function f, and the return type of f can be decomposed into ABC. And with C++26, we can decompose the result of f into ABC, and at the same time, check the condition. Of course, this only works if the return type from the function f implements an operator bool. So this is roughly equivalent to the following. So we call f, we store the result in some variable e, then in the initializer of the if statement, we decompose it into ABC, and in the condition part of the if statement, we static cast e to bool. So the new one, the first example, is much more readable. Another example of its use is if you use the stud2chars function of the standard library. Often you will write code like this, where you call 2chars and then you decompose it into a pointer and an error code in the initializer of your if statement, and then in the condition, you check if the error code is an actual error or if everything was fine. With C++26, you can now just do that inside the condition. You can decompose the result of 2chars into a pointer and the error condition and do the condition at the same time. This only works because C++26 also introduces an operator bool for the result, the result type of 2 chars, which is 2 chars result. A third improvement for structure bindings is that they can now be Constexpr, as shown in this example. A fourth improvement of structure bindings is that they can now introduce a pack. They can only introduce one pack. So let's look at an example. We have a function f here that returns a tuple containing an x, a y, and a z. So before C++26, this is valid code, of course. You can just call f and decompose it in x, y, z variables. Now in C++26, you can write something like this. So f will be decomposed into a pack with a length of 3, and that pack will contain a value of type x, y, and z. You can also combine it. You can say decompose it into x and a rest pack. In this case, the pack will be of length 2 and only contain a y and a z. If you decompose it like this, that's also valid. In this case, rest will be an empty pack. If you try to decompose it like this, that's ill-formed. You can only introduce one pack. A next C++26 feature is pack indexing, and it allows you to easily access information or a specific element from a parameter pack. Previously, that required complicated code or that is much more error-prone. Now it's rather straightforward. Here we have a function bar that accepts a parameter pack called args. And it's very easy, as you can see, to get the first element out of that parameter pack. The index can be also a constant variable. It cannot be a non-constant. So this last line will cause a compilation error. Let's look at a few more useful examples. Here we have a function template element at that accepts a variadic number of arguments, and it returns the element at a given position, I. With 26, this becomes a simple one-liner. You can call it as follows. If you call it with 3 elements, you can ask it for the element at position 0, which is 3, position 2, which is 9. And if you try to ask it position 3, then it will be an out-of-bounds error. A second example of this is this function template, structure binding element at, which accepts a tuple-like structure. And again, it returns the element at a certain index. What the function does, it simply decomposes the given tuple into a parameter pack, which we have seen a few slides back, and then just uses the pack indexing to get the ith element. So if you have, for example, a struct A having 2 fields A and B, you can easily query for the 0th element or the first element and assert that you get the right value back. Next one is hash embed. This is a new preprocessor directive which makes it very easy to pull in all kinds of data. Mostly it will be used for binary data, I think. Here you see an example where with hash embed you import a PNG file straight into an array of unsigned char. Sometimes the source from which you want to pull your binary data might have unlimited size, and for that you can specify a limit. In this case, we limit it to 255 bytes, and we are pulling data from def urandom, which is an unlimited resource on Linux. With C++26, it becomes very easy to grant friendship to all classes in a parameter pack. So if you look at this class foo, it just has 2 template parameters, t and u, and we can easily friend t and u. But if foo accepts a variable number of types, it's very hard to friend all of them. Now, with 26, you can easily do this. The syntax is you just write friend ts ... 26 adds a lot of Constexpr improvements, both at the core language level and in the standard library itself. So now I will focus on the core language additions. First one is that now in Constexpr context, you can call or you can cast from void star. This only works if the void star address points to exactly the type of object to which you're casting to. For example, again, this is contrived. We will look at a more detailed example on the next page. We have an integer v with the value 42. We store a pointer of 2v in a void star pointer, and then we can use static cast to cast it back to an int star pointer. As you can see, it's all Constexpr. And what this allows, it allows for Constexpr type erasure. And let's look at an example of that. I hope this is readable. This example actually comes from the standard proposal. So what we have here, we have a sheep and a cow with a single Constexpr member function, speak. We then have an animal view class, which, as you can see, just stores an animal as a void star pointer, and it stores a speak function, a pointer to a speak function. We have a Constexpr constructor, which stores the animal that it receives, or a pointer to the animal it receives, in the void star animal pointer. And at the same time, it constructs a speak function using a lambda. And inside that lambda, you see a static cast to cast our animal, our void star. There's a typo here. Yeah. No, it's fine. Sorry. So to cast our void star animal back to an animal star, and then call our speak function here. So this is the thing that is now allowed by C++26. And then next we just have a Constexpr speak function, just calls the stored speak function, and it passes a void star animal pointer. Next, we have a doSpeak function that accepts any kind of object that implements our animal view interface, and then you can call it, for example, on a cow, which implements the animal view interface. And it all just works, and this line, it works with C++26. Before, you will get a compilation error because static cast is not allowed. So this example is functional equivalent to standard polymorphism, but we use type erasure here, and it doesn't require any vtable. And what this will allow in the future, in future standards, this will allow to make things like std format, function ref, function any, and probably many more, to make these functionalities Constexpr in the future. And so once format is Constexpr, then we can use the static assert with computed strings that I mentioned before. Next, it's now possible to use placement new in Constexpr in constant evaluation. Just as a reminder, this is the syntax of placement new. Bigger is that it's now allowed to throw and catch exceptions during constant evaluation. So here we have a divide function. It throws an exception invalid argument when you're trying to divide by 0. And if we call it with the arguments 5 or 0, before C++26, this will result in a compilation error because we are throwing during constant evaluation. With 26, this will still result in a compilation error, but this time because we are throwing an exception and we are not catching it. So if we write another function, also Constexpr check divide, and we just wrap the call to divide in a try catch, and then when everything is fine, we return the result of the division. When we divide by 0, we return a null optional. Calling it with the same arguments 5 and 0, before C++26, still compilation error because we're still throwing during constant evaluation. Since C++26, this will compile fine because yes, we are throwing, but we're catching it in check divide, and we are transforming the exception into a null optional. One thing that C++26 introduces is a new behavior. Everybody knows about undefined behavior. There are actually quite a few other behaviors as well. New is erroneous behavior. And this always is caused by incorrect program code. What an implementation is allowed to diagnose this, but it is not required to do so. And what is erroneous behavior right now? For example, reading an uninitialized variable is defined as erroneous behavior. So here we just defined D1, and we try to read the value and store it in E1. This is erroneous behavior. Sometimes you don't want this new behavior. And if you don't want this, you can use a new attribute called indeterminate. If you look at this function f here, or the function g, it defines a y and then passes y to f. This is erroneous behavior because y is not initialized, so we are trying to read an uninitialized variable. If, however, like in this case, you define x with a new attribute, indeterminate, calling f and passing x, this is undefined behavior, not erroneous behavior. And when would you use this, for example, in this case, when you define an int variable x, and you don't care what is in there because you're going to override it anyway with input coming from std_sin, then you can just mark x as indeterminate. That's it for the core language features. That's already quite a lot. Now let's look at the standard library changes, or some of the standard library changes that are coming. First one, and this is a big one, just like static reflection and contracts, the execution control library. It's a brand new library to make it easier to work with asynchronous resources. It's all defined in the execution header. And why do we need this? Because asynchronous execution is everywhere. It's used in networking, it's used in graphical user interfaces, file I/O, accelerators, literally everywhere. Before C++26, you had functionality like std async, future, promise. These are building blocks and it's not always easy to use these correctly. So the execution control library has a couple of key design choices. The building blocks must be composable and generic to allow code to work with all kinds of different execution resources. So the code, it shouldn't think about whether it's running on a GPU or on a CPU or things like that. And common asynchronous patterns, they must be encapsulated and easy to reuse in some kind of pipeline. The whole point of this library is that it's easy to use correctly by construction, which is not the case with std async and promise and so on. During the design of the execution control library, care has been taken for all reasonable use cases, domains, platforms, and so on. Important errors need to be propagated correctly. And not only that, but it should not be a burden to handle errors correctly. And finally, the whole thing should support cancellation. There are a few key abstractions that you need to know about. First, you have the execution resource. That is a place, something, where work is executed. This can be a GPU, this can be an FPGA, this can be a thread pool, anything. Next concept is a scheduler. That is a lightweight handle that represents a strategy for scheduling work on some execution resource. In a few slides, we will see this in a practical example. It will become more clear. Next, we have a sender, and a sender is actually describing the asynchronous work that you want to execute on your execution resource. And a sender can send a signal. A signal can be either a value, if everything went right. It can be an error, if some error was encountered, or it can be stopped if a cancellation was requested. And that signal is then sent to a receiver. And the receiver basically serves as a glue between the different senders. It's basically a callback supporting set value, set error, and set stopped. A bit similar like std promise. Std promise supports set value and set exception. These schedulers and these senders are defined by the standard as concepts. Next, we have several asynchronous algorithms. We have sender factories, sender adapters, and sender consumers. So let's look at them one by one. Sender factories, they are algorithms that take no senders as parameters and they return a sender. So the first example here, execution schedule, that's actually a sender that starts the whole task graph. We will see that in an example. We have a sender factory execution just. That is just a sender without any completion schedulers. It just sends a given value. And just error, similar, it just sends a given error. Sender adapters, it takes one or more senders as its input, and it returns another sender whose completion is related to the input senders. One example is continuous on. That is a sender that allows you to transition from one execution agent to another. Then is a sender that invokes a given callable with the result of an input sender. And there are many more. You have starts, on, when, all, and lots of other sender adapters. And finally, the final asynchronous algorithm is a sender consumer. That takes one or more senders, and it doesn't return any sender. So the standard defines only one. It's defined in this thread sync wait. It's a sender consumer that just submits the work that you've constructed, and it just blocks until its execution is finished. Let's look at an example. So the first thing you need is a scheduler. It all starts with a scheduler. So here we just use a thread pool scheduler. Work on a scheduler is started by calling this schedule method, which returns a sender on the scheduler. And then we can add work to this using the then sender adapter. So this thing accepts a callable, and our initial sender, it doesn't return anything. So the lambda that you pass to our sender adapter doesn't accept any parameters. In this case, the lambda just prints something to the console, and it returns an integer. We can then add more work, again with then, and since our previous sender returns an integer, this new the new sender adapter, the lambda here, must accept an integer. It must accept what the previous sender in the pipeline is returning. In this case, this sender adapter just returns whatever it receives and adds 42 to it. And then finally, we can start the whole execution. For this, we use this thread sync wait sender consumer. So it just triggers the execution and waits for the execution to finish. So up to this point, up to this call, maybe nothing has executed yet. It's all asynchronous. Maybe execution is finished, maybe not, we don't know. But here we just wait until the execution is finished. All right. C++26 introduces two new containers, in-place vector and Hive. So first let's look at in-place vector. It's defined in the in-place header file. It's a dynamically resizable vector, but with the capacity fixed at compile time. And it uses contiguous in-place storage. What does in-place storage mean? It means that the elements for the vector are stored within the vector itself. Why is this useful? Well, sometimes memory allocation is not possible. It can be expensive or not. Expensive, that's the second one. Maybe it's not possible. Maybe on some embedded systems you cannot allocate memory. And maybe you require that the storage of the elements must be in place, for example, if you want to serialize with memcopy. So what is the difference with std array? An in-place vector Tn can store up to n elements, while a std array always stores n elements. So in-place vector is dynamic. Simple example here, we define an in-place vector with capacity 3, so fixed at compile time. We store 2 elements in it, so the size becomes 2. We store a second or a third element in it, size becomes 3. If we try to put a next element in there, we will get an exception. An exception of bad alloc will be thrown. If you don't want exceptions in your use case, you can use try pushback. If you do this on a vector that is full, it will return null PTR. It will not throw any exception. Hive is the next one. So it's defined in Hive. It's typically known as a bucket array or an object pool. The concept is that you have multiple memory blocks of elements, and every element has a Boolean to say whether the element is still valid or has been deleted. This is typically called a skip field. Why skip field? Because if it is true, that means the element is erased. That means it will be skipped over during iteration. When all the elements in a block have been deleted, then that whole memory block is deallocated. And if all the blocks are full, then we just add a new block. So let's look at it graphically. So here we have our Hive. If you zoom in, you will see there are multiple memory blocks, block 1, 2, 3, with a number of elements in there. And all the red elements are erased, so these are ready to be reused for a next insertion. How exactly an implementation implements this skip field that is not defined by the standard. Benefits, there are no reallocations when you erase something. If the hive is full and you need to allocate a new memory block, there are no reallocations of existing elements. So basically, all element memory allocations stay stable and iterators stay valid, even if you erase or insert something. Using it straightforward, if you use any of the other containers, you can use hive. So we define a hive here with 2 elements. We add 2 additional elements, and then we just print it in a range-based for loop. C++23 introduced mdspan, and now 26 introduces a new function, submdspan, which returns a view of a subset of an existing mdspan. So let's look at an example. We have a function here, 0 to 2D grid, which accepts a rank 2 mdspan. And a rank 2 mdspan is 2-dimensional grid. It just loops over all the elements and puts all the elements to 0. And then we have a function called 0 3D cube surface, accepting a rank 3 mdspan, which is a 3D cube. And what the function does, it is going to put all the values of the sides of the cubes to 0. And to construct a view of the 6 sides of the cube, it uses the submdspan function. Next, we have saturation arithmetic. So normally, if you do arithmetic, it's modally 2n. Now with 26, you can also do saturation arithmetic. There are 4 new functions defined for this to add, subtract, multiply, and divide values using this saturation arithmetic. Let's look at an example. If you are representing pixel values as unsigned char, then 255 means it's a white pixel. If you want to brighten an image, or this pixel, and you add 4, for example, to it, with normal arithmetic, the result will be true, which will not be bright at all. It will be very dark, actually. So in this case, you use the new function add set to use saturation arithmetic, and then when you add 4 to 255, you get 255. All right. So 26 allows construction and reinitialization of string streams and bit sets using a string view. So this line of code, that already works. So you can construct a string stream from a string. You can now also construct it from a string view. You could already reinitialize it using a string. Now you can reinitialize it using a string view. And similar for bitset, you could already construct one from a string. Now you can construct one from a string view. Text encoding is also new. It allows you to retrieve the text encoding used by literals in your code and the text encoding used by your execution environment. Simple example, function here that verifies if your environment supports UTF-8. A more complicated example, we have a function print suffix that prints a duration to an output stream, a duration in microseconds, and we would like to use the actual micro character if it is supported by your environment. Otherwise, we fall back to outputting US. So first, we check if the literal encoding is UTF-8. If that is the case, we check if the encoding of the output stream supports UTF-8. And if that is the case, then we actually output our micro character. Otherwise, we fall back to outputting US. Native file handles. C++26 provides access to the underlying OS native file handle for output streams, or any kind of stream. It's defined by a new type alias. It's called native handle type, and your compiler will map this to the right type for your OS. For example, on POSIX, it will be mapped to int. On Windows, it will be mapped to a handle. And then the basic classes, basic file buff, ifstream, ofstream, and fstream, they all have a new method called native handle that returns the native OS handle to your stream. Let's look at an example. Here we have a last modified function that is using the POSIX fstat function to get some information about a file. So that requires an an int. So this function accepts an int, a file descriptor. Then in main, we use an OF stream to create an output stream for file foo.txt. And if we want to call our function last modify, we need to pass it the file descriptor, so the underlying native handle. And so we just call native handle and pass that to last modify. As mentioned before, C++26 introduced a lot of new Constexpr functionality. Core language, standard library, the core language we already discussed. Let's look at what's new in the standard library. First thing, these stable sorting algorithms, stable sort, stable partition, in-place merge, they are now Constexpr. So using them is not different as currently, so I'm not going to show an example of that. The CMAT and the complex headers, they have much more Constexpr functions. You have functions such as the trigonometric functions, many, many more. They are all Constexpr now. Again, using those is trivial, so I'm not going to give an example of that. Most methods of std atomic and std atomic ref are now Constexpr. The specialized memory algorithms like uninitialized value construct, uninitialized copy, uninitialized move, they are all Constexpr. As we've seen earlier, you can now throw and catch exceptions during constant evaluation. And for that, all the standard exceptions such as bad cast, invalid argument, and so on, they're all Constexpr now. Finally, all the containers and all the container adapters are now Constexpr. That includes DEC, priority queue, map, span, in-place vector, all of them, except for the new Hive, that is not Constexpr. In 2022, there were 4 new SI prefixes adopted. So C++26 now adds them to the C++ standard, and these are for extremely small or extremely large numbers. They are called, know how to pronounce them, Quetta, Rona, Ronto, and Quecto. An implementation only defines these if the int max t of the implementation can represent the denominator or the numerator. This is nothing new. The existing Yocto, Zepto, Zeta, and Iota, they're also conditionally defined only when the int max t of that platform supports them. Debugging, there is a new debugging header. You can now easily and platform independently check if a debugger is attached. You can programmatically trigger a breakpoint, or you can programmatically trigger a breakpoint only if a debugger is attached. All of that is now platform independent. New header, linalg. It introduces a whole set of free functions for linear algebra computations, and it is based on the basic linear algebra subroutines library. C++26 only supports a subset of the BLAS standard. So it supports these things like element-wise vector sums, multiplying all elements of a vector or matrix by a scalar, and so on, including generating and applying plane rotations. So this is all very mathematical, so I'm not going to give a detailed example of this. I'll just look at a very trivial example in a couple of slides. But let's first look at what are the features of this new library. So it uses free functions. It doesn't use overloading, operator overloading. To represent matrices and vectors, it uses std_mdspan, which was introduced in C++23. It allows implementations to optimize for matrices and vectors with small compile time dimensions. An implementation must support mixed precision computations with matrices and vectors that have different element types. And finally, it must be possible to provide an execution policy to every function to allow the implementation to vectorize it or parallelize it. Let's look at an example. Here we define a vector of 40 elements. We then use the existing IOTA algorithm to just fill the vector with the value starting from 0, so it will be 0, 1, 2, 3, and so on. We use std_mdspan to create a view on our data, so this view will be the sequence 0, 1, 2, 3, all the way to 40. Then we use one of the new linear algebra algorithms called scale, and we scale all the values in our vector by 2. So this result in 0, 2, 4, 6. We can do it again, we can scale again, and this time we pass a execution policy par unsec to multiply everything by 3, so the result is 0, 6, 12, 18. New in C++26 is that you can access complex values as if they are tuple-like values. And what this allows is you can use structure bindings for complex values. For example, in the past, you could do something like this. You can use a reinterpret cast to cast a double to an array of doubles, of 2 doubles, and then you can use a structure binding to decompose it into the real component and the imaginary component. This is ugly, and yeah, this is not very readable. With C++26, it's trivial. You can just decompose your complex value into the real and the imaginary part. '26 introduces a new view factory. It's called views concat. So what does it do? It takes any number of input ranges and it returns a view that is the concatenation of all the elements in the input ranges. For example, we have 3 vectors here, initialized with some values, and we have an array. We can then use the views concat view factory to concatenate the 3 vectors and the array together in one big view, and if you would print that, you get the elements 1, 2, 3, all the way to 8. There are new overloads for operator plus to allow concatenation between string and string view in both directions. So in this example, we define a string and a string view, and you can see that you can add a string view to a string, or you can add a string to a string view. Both work just fine. List initialization for algorithms. Let's immediately look at an example. We have a simple point struct here with 2 fields, x and y, and we have a defaulted operator equal equal. We define a vector of points. If you want to put a point in our vector, you can just write it like this. So you can already use list initialization to add a point to our vector. But if you want to call algorithms like find or fill, you had to specify the point type. With C++26, you no longer have to do that, and you can actually use list initialization for set find, for ranges fill, and for all the other algorithms as well. There is also a new view adapter to cache the result of a last dereference of an underlying iterator. Sounds complicated, but let's look at an example. We first define 2 lambdas, a square that simply prints something to the console and returns the square of an input value. Second one is even, again, print something to the console and returns true or false depending on whether the input is even or not. We create a vector of 5 elements. We then use views transform to square all the elements, and we use views filter to only keep all the even values. If we now output that, remember we are outputting something in our lambdas here. If we output this, you will see that transform is sometimes called multiple times for the same element. So here, transform is called for 2, and here again, transform is called for 2, and the same for 4. So sometimes this might not be optimal performance-wise. So in C++26, you can fix this. What you see here is exactly the same code as on the first slide. Nothing has changed yet. The only thing that we change is we add the single line cache latest. If you now look at the output, you see that transform is only called once for all of the elements. There is also a new range-based algorithm to fill a range with random numbers. It's called ranges generate random. So in this example, we are defining an array of 42 integers. We define a Mersenne twister and seed it with a value from a random device. We define a uniform in distribution to only generate numbers between 0 and 100. And then we use a new std_ranges generate random algorithm to fill our array with random numbers generated by this Mersenne twister. Of course, there are also iterator-based overloads. And talking about random numbers, this is the first time since C++11 when they introduced the random header. It's the first time that a new random engine is added to the standard. In this case, we're adding the Filux engine. There are two predefined engines. You have Filux 4x32 and 64. What are the benefits? They have a very small state, so the Filux 4x32 has only 10 32-bit elements. They have a very long period. Filux 32 has a period of 2 to the 130. They're easy to vectorize and parallelize, so well suited for CPUs, GPUs, FPGAs, and whatnot. And they are already very broadly used in research for Monte Carlo simulations. Using them is straightforward if you can use any of the other random number engines. So here we just create a Filux 4x32, seed it with a value from a random device. We use a normal distribution, and we generate a random number using that new engine and the normal distribution. With C++26, it becomes easy to format a file system path. So you can format it with std format, print, println, and so on. So in this example, we create a path for user bin. We output it using std format, and you get the output that you expect. This all works with UTF-8 file names, as well as you can see here. This example was executed on Windows. C++26 introduces a very small little new feature. In fact, I was surprised it wasn't there at the time when they introduced println in C++23. If you want to print a blank line, up to now you have to do it like this, println, and specify empty quotes. C++26, you can omit the empty quotes. Small feature, but I think it's very nice. And finally, there is a new header called SIMD. It defines a bunch of data parallel types and operations, all in a portable manner. So we have two data types. We have data par SIMD and data par SIMD mask. SIMD mask is basically a SIMD data type where the type is a Boolean. And we have a whole bunch of overloaded math functions that work on such data in parallel. And all these operations can take advantage of the SIMD instructions that are available on all of the latest CPUs. This is, again, a rather complicated topic, so I'm not going to in too much detail. Let's just look at a very easy example. So here we define a SIMD X. We define X of type SIMD. In this case, it's 16 doubles. It can be initialized using this syntax where you just pass the lambda. And if you can also just pass SIMD values straight into println or format to output them. And in this case, you will see that they are initialized using this lambda. The result will be 0, 1, 2, 3, all the way to 15. And then we can use overloaded math functions that are all defined in SIMD. Here we are calling some trigonometric functions. Actually, we're calling this formula. If you apply this to all these values in our sequence, then the result is that all of them will become 1. And you can see if we output it, you get a sequence of 16 1 values. Sorry. All right, that's it. That was an overview of a lot of new updated core language features and standard library features. But this overview is far from exhaustive. The C++26 standard is really, really big. Just to give you kind of a sneak preview and a lot of keywords if later on you look at the slides. There are many more core language updates. You have things like unevaluated strings. We're adding some new characters to the basic character set. We're removing several features. I didn't actually exhaustively list what we are removing. There's this thing called Oxford variadic comma. We have trivial unions, observable checkpoints, and many more. And that's only additional core language features. We're not even looking at additional standard library changes. That's this. It's a huge number of even more changes to the standard library that's coming with C++26. It includes things like hazard pointers and read copy update, There are lots and lots of updates for freestanding functions. There are additional changes to the ranges library. We have the standard library hardening, and many, many, many more. So have a look at these slides later, and you have a lot of keywords. You can search more information for it. So to conclude, C++26 is a very big update. So that's it. I have a few minutes left for questions.
Hello. So you said that the algorithms accepting just list initialization instead of actually requiring like the type to be specified is a library feature. Was that facilitated by expanding the rules of the language, or did they just add new overloads that are more generic somehow, or how did they allow that?
I'm not entirely. It must be the latter one.
Okay.
It's pure a standard library update.
Okay.
How
Maybe
exactly
initializer list or something.
Sorry.
Maybe initializer list.
Maybe
or-
I don't know exactly how they done it, but it's pure in the standard library. It's no core language changes.
Okay. Thank you.
So I have a question about the initializer or the unpacking in if statements. So I'm not really clear about the syntax. You said that this is, I can drop now the second statement in the if, but on what is the if condition actually evaluated? On the last element in the unpack or on the return of the function?
Return of the function. So in this case, we have a function f that returns some kind of data type, which can be decomposed into, in this case, A, B, and C. But that data type that is returned must support an operator bool.
Okay.
And you can see that also on this example here. So to chars, it actually returns a data type called stud2 chars results. This is not new. This was already the case before. But what C++26 adds is an operator bool for this data type. So then if you call it like here, it is being decomposed into a pointer and an error code, but the condition is actually going to call operator bool on the return type. It's maybe easier to see on this slide where here, where I'm decomposing and the condition in one, it's roughly equivalent like this. So we call our function f, we store the result of f in E, and the type of E is exactly the type what the function f is returning me.
Okay.
And then in the initializer of the if statement, we are just decomposing it into ABC. And in the condition part, we're calling static cast bool of E. So this type must support this.
Okay, thanks. I didn't got this roughly equivalent to. Thank you very much.
Yeah.
Hello. For the Hive container, I just wanted to know, like, what is the time complexity for random access and to iterate through it?
Sorry, the time complexity of?
For the Hive container, time complexity of random access or accessing, like, based on index?
Right. So as you can see, find the Hive. So the Hive exists of several disjoint memory blocks, right? They can be scattered into blocks in memory. But yeah, I guess it's not mandated by the standard how they are implemented, but I guess one block will point to the next block, will point to the next block. So iterating over them is,
Linear?
Yeah.
Okay.
Yeah. And yeah, benefit again is there are no reallocations happening ever. So if you have like an iterator to one of the elements, it stays stable.
Right.
Even if you add elements to your Hive, or if you delete elements to your Hive, it stays stable.
Got it. Thank you.
All right, I think we're running out of time, but you can always find me in the hallways or after this talk. Thank you.